Hey everyone, so today we're going to go over some practice problems for Newton's second law of motion. So for the first example, let's say we have a box. Say we have a box that's 10 kilograms and we have a force acting on the box of 60 newtons. What is the acceleration acting on the box? Well, we simply put it into our force equation, which is that force is equal to mass times acceleration. And then we isolate for acceleration. Force over mass is equal to acceleration. We plug the values in. 60 newtons over 10 kilograms is equal to 6 meters per second squared east, or to the right. So our acceleration is 6 meters per second squared to the right. Let's go over one more problem like this, and feel free to try it on your own. But let's say we have a 13 kilogram box and we have a force of 55 newtons acting on it to the left. And then we have a friction force. The first one was on a frictionless surface. This one's on a surface with friction. We have a friction force of 17 newtons going to the right in the opposite direction. What is the acceleration of the block, and in what direction? So first, before we can plug this into the equation, like the first problem, we have to find the net force. So F net is equal to 55 minus 17, which is equal to 38. So our net force is equal to 38 newtons. And then we can plug that into our equations. So F is equal to ma. F over m is equal to a. We go 38 newtons over 13 kilograms, and that is equal to 2.92 meters per second squared west, or to the left. Now let's try a different problem. What average force is required to accelerate a 10 kilogram box from rest to a final speed of 63 meters per second in 9 seconds? So first, let's draw this out. So we have a box. It's 10 kilograms. And we have a force acting on it. Now, it's asking us for the force needed to go from rest to 63 meters per second. So if we write out our givens, our initial speed is 0 meters per second. Our final speed is 63 meters per second. Our mass is equal to 10 kilograms. And our time is equal to 9 seconds. What we're looking for is F. So first we have to find the acceleration. And if you know your kinematics, Vf is equal to Vi plus At. Now since Vi is 0, we can cross that out and keep it Vf is equal to At. And now we rearrange for time to isolate for time. Vf over T is equal to A. And then we plug it in, 63 meters per second over 9 is equal to 7 meters per second squared as our A value. And then we can plug it into our force formula. So F is equal to ma. F is equal to 10 kilograms times 7 meters per second squared. F is equal to 70 newtons. Now let's try one last example. You have a 2,000 kilogram car moving at a speed of 18 meters per second, and it comes to a stop after traveling 200 meters. What was the average force exerted by the brakes on the car? So first, let's draw this out. I'm going to draw the car as a box. We have 2,000 kilograms moving at a speed of 18 meters per second. And then you have a brake force, which we don't know, and it's what we're calculating. Now before we write out any formulas, let's write out our givens. So our V initial is equal to 18 meters per second. Our final velocity is equal to 0 meters per second. Our distance is equal to 200 meters. Sorry, let me just rewrite that. It's equal to 200 meters. What we don't know is our acceleration and our force. Now once again, we have to find our acceleration first. So we can use Vf squared is equal to Vi squared plus 2AD. Now we rearrange to isolate for A, so Vf squared minus Vi squared over 2D is equal to A. We plug that in, we get 0 minus, you get 0 minus 324. 324 over 400 is equal to negative 0.81 meters per second squared, which makes sense. The reason it's a negative is because we're braking, so the force is in the other, or the acceleration is in the other direction. So that makes sense. That's equal to A. And then we can use that into our force formula. Force is equal to mass times acceleration. Force is equal to 2,000 kilograms times negative 0.81 meters per second squared. Force is equal to 1620 newtons. So the braking force is negative 1620 newtons in the direction, which indicates the direction is opposite the way the car was going.